Hi everybody, I'm Greg Fishel. This is bonus weather video number 1 for this week, and we haven't done one like this, or I haven't done one like this in a while. This is very, very math intensive. So if you absolutely despise math, you might want to bypass this one. But I will say this, is that a lot of people, not all, but a lot of people that just despise math, I think do so because they've never had it really explained to them in a clear and understandable way. And I'm not saying that I can do that. I'm going to try today. But I think, it was like me in history. I never enjoyed history until I had this instructor when I got to 7th grade, and he completely changed my opinion about history. I mean, because he made it interesting, he made it fun. And again, I'm not saying I can do that, but I will try over the course of the next several minutes. So when you watch a weather report on television, or you look at a website or whatever, and you're looking at what the conditions are currently, and you see the air pressure, do you know that that's not your actual air pressure? Okay. Now, it's not that any of these people are lying to you. It's just that if we only looked at the actual pressure at all the stations around the world, all the low pressure areas would be over the mountains and all the high pressure areas would be over the ocean. Well, we're not interested in getting a topographical map of the world. We want to know where the weather systems are. And so we have to standardize those pressures by doing something called reduction to sea level. And so we're going to talk about how we do that, and also how we can still make calculations even for places that are just far enough above sea level so that it creates some issues, okay? So we're going to talk about both of those things as we go along here. So let me put myself down here in the corner, and let's start with this. A little fun with math. And for those of you that don't like math, fun is probably not the operative word. Now, there is an equation in meteorology called the hydrostatic equation. The simplistic answer to this, or description of this equation, is that there is a balance of two forces on our atmosphere. One is gravity, which is pulling it down. The other is what we call the pressure gradient force, which operates from high pressure to low pressure. And we know that the pressure goes down as you go up, and so that force is directed upward. And you can assume this on a large scale. On small scales you can't, but on the large scale you can. And this is why the atmosphere doesn't collapse into the ground or escape to space, okay? And so the way you represent this mathematically, and by the way, this little symbol here in front of the P, which stands for pressure, and the Z, which stands for height, all that means is change, okay? So the change in pressure compared to the change in the height is equal to this, okay? And so that's all that is. Yes, it's a differential equation in calculus, but all you need to know is that it means change. Okay, so P is equal to pressure, Z is equal to height, the Greek letter rho is equal to density, and g is equal to the gravitational constant, which is the rate at which objects accelerate as they approach the Earth, which is 9.8 meters per second squared, or 9.8 meters per second per second. Now, there's another equation called the equation of state, and that states that the pressure is equal to the product of the density times R, which is a gas constant, times the temperature, okay? Well, if we solve that equation for the density, we get P over RT. Well, we can substitute that into this equation where you see the Greek letter rho, density. We can substitute this up here. And so what do we end up with? Well, we end up with dP dz, same thing you got up here, is equal now to minus the pressure times the gravitational constant over RT, okay? Now, there's something in calculus called integration, okay? But before I get to that, we're going to divide both sides of this equation here by P, okay? So this is going to go down here, and we're going to multiply both sides of the equation by dz, which is going to get rid of this and put it over here. So we have dP over P is equal to minus g over RT. Then you can do what's called an integration, where we're going to integrate this equation from one level to another level, okay? So on the left side of the equation, we're going to go from a pressure which is near the ground to a pressure that's a little bit higher. And over here, we're going to go from a height, which is at the ground, okay, or near the ground, to a height a little higher. And there's a little mathematical trick that if you want to get rid of this minus sign here, you simply swap these P2s and P1s. So now you're integrating from P2 to P1 instead of P1 to P2, and you're integrating still over here the same thing, Z1 to Z2. Okay, you with me so far? Now, when you integrate that, what you end up with is this, is the natural log, okay, natural logarithm of pressure 1 to pressure 2 is equal to G over RT times Z2 minus Z1, which is the distance from P2 to P1, okay? And we call that the thickness. And thicknesses are very useful in meteorology for a number of reasons. You can use them to estimate what the high temperature is going to be. You can use it to estimate where boundaries between rain and snow and ice are going to be. Not that that's been important in North Carolina for a couple of years now, but it is very, very useful in doing that. Okay. So P1, we're going to say that P1, which is the pressure nearest the ground, is 1,013.2 millibars, which is standard atmospheric pressure. Okay, there's what's called a standard atmosphere, and that's the pressure in a standard atmosphere. P2 is going to equal 1,000 millibars, so just a little bit above the ground. We're going to say the temperature is freezing, which in Kelvin is 273.15. G is the gravitational constant. We've already talked about that, 9.8. R is equal to 287, which is the gas constant. And so when you do all the math, you get 0.013114 is equal to 0.000125 times the thickness, which again is the distance between these two pressure surfaces. And you come up with a thickness of 104.912 meters, okay? Now, how much did the pressure change from 1,013.2 to 1,000? Well, it changed 13.2 millibars, right? So, if we take 104.912 meters and divide it by 13.2 millibars, what we do, or what we come up with, is a conversion factor which says 7.95 meters is equal to about a millibar. And I'm just going to round this off to 8 meters per millibar. That's the general assumption that's made in the lower part of the atmosphere. Now, as you go higher and higher, it takes more distance to go down the same amount of pressure, okay? Because the atmosphere is less dense up there. But near the ground, 8 meters per millibar is a fair estimate. Now, if 1,000 millibars, well, let me, before I get to that, I should have reversed the title and what I'm going to talk about here. This is the actual observation when the weather balloon carrying the radiosonde up through the atmosphere near Greensboro today, this is what they came up with. And I want to highlight two numbers here. 991 is the station pressure, so that's the actual air pressure at Greensboro at 7 o'clock this morning, 991 millibars. And this is the height of the 1,000 millibar surface. And you're sitting there going, now wait a minute. If the station pressure is 991, then there is no 1,000 millibar surface, right? Because the pressure can't be any higher than what it is at the ground. Well, we still like to make calculations like 1,000 to 850 millibar thickness. So what we do is we use a standard atmosphere and project how far underground that 1,000 millibar surface is going to be, okay? So it is saying that it's 197 meters above sea level. So how did they come up with that? Well, the station pressure is 991 millibars, and we want to know what the height is above sea level of 1,000 millibars. So that's a 9 millibar difference. We take 9 millibars times 8 meters per millibar, and we get 72 meters. Well, if the station pressure, or I'm sorry, the elevation above sea level at Greensboro is 270 meters, and the 1,000 millibar surface is going to be below, okay? In other words, if at 991 millibars, the elevation above sea level is 270 meters, so we're going to have to go lower than that. And so if you subtract 72 from 270, you get 198. And here it's 197. Now, they are probably working with much more precision in their actual numbers, and this is why they got 197, I got 198. Obviously very, very close, okay? So that's how the 1,000 millibar surface is calculated, even though it is underground, if you will, but that's how far it is above sea level. So that allows us to continue to make calculations, even in a place where the pressure is less than 1,000 millibars, and come up with these thickness values, which are still very useful. Now, this is only useful at places that are reasonably close to sea level. You get out to Denver, where you're a mile above sea level and the whole layer is underground, that's useless, okay? And so they probably would deal more with like an 850 to 700 millibar thickness out there, because they want to deal with as much air as they can and not rock and mud, okay? All right, so how do we get from the station pressure to the sea level pressure? Well, this was the actual observation at Greensboro at 7 o'clock this morning, same time they sent up the weather balloon. And right here it has SLP 232. Now, whoever came up with this code had a nightmare one night and wrote it down when they got up, okay? But SLP means sea level pressure. If the 232, if that number is less than 500, you put a 10 in front of it and a decimal point before the last digit. If it's greater than 500, you put a 9 in front of it and a decimal point before the last digit. So the sea level pressure is 1,023, put a 10 in front of the 232, and a decimal point before the last digit, 1,023.2 millibars. Okay, the station pressure is 991 millibars, and the station elevation is 270 meters. So we know that 8 meters is equal to a millibar. So if we divide 270 meters by 8, we get 33.75 millibars, and we add 33.75 to 991, and we get 1,024.75. Again, not an exact match for 1,023.2, but you can see that basically this works. And again, they're probably dealing with precision out to many decimal places when they do these calculations, which is why my number is slightly off. But you can certainly see the relationship here, okay, as to how you get that sea level pressure from the station pressure, okay? So when you see a pressure on a TV weather show or on a website or whatever, that pressure has been altered and reduced to sea level so that we can tell where the actual weather systems are, and it's not dependent on elevation, okay? And that's very, very important in being able to see where the various weather systems are. Okay, I know that was a lot of numbers, a lot of equations. Hope it was at least mildly interesting to some of you. I'm shaking when I say that. But anyway, that is bonus weather video number 1 for this week. And bonus weather video number 2 will be coming up on Wednesday, and the daily weather update will be coming up later this afternoon. Should have no problem getting that out by 6 or before. So, and now that I'm producing these bonus videos earlier in the day, it is allowing me to get those daily updates out earlier, which I know is important to all of you. Okay, that's it for now. You have a wonderful Monday evening, and we will talk to you again later today with the daily weather update. See you later, everybody.